Hi everyone. The first video is going to discuss the basic concept of trends that we talk about in class. I just want to review that again so that when we talk about the trends observed in electron affinity energies and other trends, you can refer back to this video to remind yourself of what we consider. So the main equation to keep in mind as far as trends is concerned is the equation for the binding energy, which is shown right here. The binding energy, which is the energy of an electron that's holding the electron together in the atom, and usually this is used to refer to the valence electron, the energy that holds the valence electron in the atom, is given by the following equation. Negative RH, which is the Rydberg constant, times Z effective squared over N squared. Okay, so then the energy of a valence electron will then depend on two factors. One is the value of Z effective, which, remember, this is a number that depends on where the electron is located in terms of principal quantum number, as well as what kind of orbital it's occupying, its L value, okay, whether it's S, P, D, or F. And then the second component of this equation is the principal quantum number itself, which is shown as the denominator. The interplay between the Z effective and the N squared is what results in the energy of the electron, and that will then shows us what the trend will be observed for ionization energy, for electron affinity, and so on. So let's discuss these two factors in terms of trend across a period as well as trends across a group. Okay, first off, let's discuss a period. If you're going through a period, which is from left to right in the periodic table, the trend will mostly depend on the value of Z effective, and I will explain why. If you look at these three atoms, for example, these three elements are all in the second period. So in other words, n is equal to 2. Now if n is equal to 2, as you go to bigger and bigger elements in this second period, what you're doing is you're basically increasing the size of the nucleus, right? So for lithium you have 3 protons, and that's why your nucleus has a +3 charge. For beryllium you have 4 protons, so as a result your nucleus has a 4+ charge, and then if you keep going further up, then for fluorine you're going to have 9 proton, and as a result your nucleus would have a +9 charge. As we're adding the protons, we're also adding electrons, but remember, the basic structure looks the same. In a second period element, you're going to have your 2 1s electrons, right? So remember the configuration is always 1s2. So all of these would have 2 1s electrons. That's illustrated by the smaller circle right here. That's the n equals 1 level. And then, as you go to bigger and bigger atoms in the second period, you're just going to add more and more electrons. I'm just going to give them slightly different colors to differentiate the 1s and the n equals 2 electrons. So for lithium, I only have 3 electrons, so then only 1 more, and that's located right there. For beryllium, I have 2 more electrons located right here and right here, let's say. And then for fluorine, I'm going to have 7 more electrons to make my 9. So then I'm going to put in 1, 2, 3, 4, 5, 6, 7. Okay? So as you go left to right, the only thing that's changing is the proton. That's the factor that changes the most. The number of electron changes, however, all these valence electrons are being put in the same shell. The shell level is n equals 2, right? So in other words, you're not making the shell size any bigger. You're not going to further shell. You're just staying at the same shell level, n equals 2. We go back to our equation, our main equation right here. What you see is that the n value stays at 2, which is 2 squared in this case, right? But the Z effective changes quite a bit because as you go, your shielding is still just shielding by the first electron, by the first 1s electron, right? This is your shielding right here from the nucleus. So this shielding is primarily done by these core electrons. So even as you go bigger and bigger size of nucleus, the shielding is the same. It's pretty much done by these 2 electrons in the 1s orbital. The rest of the other electrons, these electron, that electron, this electron, they repel each other in that n equals 2 level, but the amount of repulsion is not as great as the shielding that's done by the 1s electron. As a result, the value of Z effective as you go from lithium to beryllium to fluorine gets bigger and bigger and bigger because the value of Z, the nuclear charge itself, is also increases. As a result, if I go back to this equation, my n value stays constant, my Z effective goes up by quite a bit. as I go from left to right. Okay, so across a period, let me just summarize this again. The factor that will govern the trend is the value of Z effective. The reason for this is because the n value stays relatively constant. Okay, let's now talk about elements down the group, right, in the periodic table. The trend will be governed primarily by the value of n, or the principal quantum number. Why is that? Let's take a look at an example here. If, again, I'm looking at lithium, okay, I have 3 protons and 3 electrons. And as I was drawing earlier, I show that my 2 electrons are located in here, okay, and then my valence electron is located right here, okay. Now, if you go to the next element in the group, which is sodium, you're going to have 2 electrons here, then you're going to have 8 electrons in the second shell, and then you're going to have 1 electron as the valence electron in the third shell, okay. So you can see what happens here is that it's true as I go from lithium to sodium, I go from a 3 proton, 3 electron system to an 11 proton, 11 electron system. But the valence electron location is quite different. Here the valence electron is located in n equals 3. Here the valence electron is located in n equals 2. Now if I keep going to go down to larger atoms in the group 1a element, when I get to something like cesium, for example, I would have the following. Here's the nucleus. Here's 1, 2, 3, 4, 5, and 6. Okay? Cesium is in period 6, so it's going to end at 6s1. All of these guys, you're going to have electrons in the core positions. All of these are filled with electrons, right? I'm not going to draw all of them. Okay, I'm just going to draw some of them. But all of these are filled with electrons. So you can imagine that you have 1 level filled with electron, 2, 3, 4, and 5. So now you have quite a bit of shielding. All of these purple colors shielding the valence electron, which is right the outside right here, from the interaction with the nucleus. Now it's true. The nucleus here is a plus 55 nucleus, right? Which is pretty strong. But you also have a lot of shielding that's happening. So think about it. The value of Z, not Z effective in this case, Z goes up. But the value of Z effective depends on the amount of shielding you have, as well as if there's any penetration in terms of the orbital. But we're comparing the same type of orbital, which is the s orbital, right, for the valence electron. So the penetration effect is the same. What we're concerned about here is the shielding effect. As you go further out, there's more shielding. So in other words, even though the Z goes up, because of shielding, the Z effective actually only goes up a little bit. Okay, so I'm representing it by a smaller arrow here, just to show that the Z effective, even though it goes up, it doesn't go up by as much as you thought it would be because of all this shielding issue. Okay, however, the other thing that clearly goes up is the principal quantum number. By the time you get to cesium, your n value right here is n equals 6. Okay, so you've gone from n equals 2 to n equals 3 to n equals 6. Okay, as you go down that group. Now what happens if you go back and look at the equation? Here's the original equation. You see that the n value, if you go down a group, the n value goes up. It goes up by quite a bit. The Z effective, as we just make the argument, is actually it goes up, but it goes up by a small amount. Nothing to the extent that these guys goes up. The n value goes up. As a result, if you take both of these factors into account, the energy value would be a constant times some number that goes up by a little bit divided by another number that goes up by a whole lot, which means that your ENL, as you go down a group, right, your ENL down a group will be smaller and smaller and smaller, or another word for it is it becomes less negative, okay, as you go down the group. What does that less negative means? Less negative just means that it's less stable. Remember, the more negative an electron is, the more negative its energy, the more stable it is because it's lower value. However, the less negative it is, the more unstable it is. So in other words, your electron becomes less and less stable, and as a result, that affects its other properties. So I want you to really understand this concept of the interplay between Z effective as well as N, okay, these from this equation, and we would apply it to all the trends that we would discuss. And I already talked about this in lecture for ionization energy. I'm going to use it to explain the trend that we observe for electron affinity, atomic radii, and ionic radii.